Well, hello, welcome to a screencast in which I'm going to try to describe the basics of LC circuits by using a mechanical analogy that we studied back in our mechanics unit. This is exactly the same kind of discussion that Dr. Knight has in his book, so it's not really going to do much different other than maybe amplify a little bit some of the points that he's trying to make. I am going to use a diagram that my previous textbook used. This was out of Halliday, Resnick, and Walker. And I think it's kind of nice because it shows a complete cycle with an LC circuit. So just talk about the players that we have here. We start with a capacitor and an inductor. That's just a solenoid or a coil. And we're going to start here in figure A on the left. And what it shows is a fully charged capacitor. I'm just going to put a couple of charges in here to remind us that the top is positive in that instance. I can tell that because the electric field lines are pointed downward. And at this point, because it's fully charged, we have no current flowing at the moment. And we don't worry about how the charges got there. We just say for some reason there's a fully charged capacitor that we connected electrically to a coil. So what's going to happen here? Well, because charges don't particularly like being crowded on the same plate of a capacitor, it's going to try to discharge if it can. This is just like when we discharge the capacitors in the lab. We touch it to a piece of metal on the sink faucet or something, or our hands even would work. But now we're going to send it through a coil. And the nature of a coil is it's got this inductive property, which means you can't just immediately zoom current through it. It has to slowly build up current and then slowly diminish the current. And we will do that by the time we get halfway through the cycle. We will have increased and then decreased the current, but it has to do so slowly. And so that's what we see here in B. We're building up a little bit of current in the inductor, and I can see that by the magnetic field lines increasing through there. And we've reduced some of the charge on the capacitor. And then here in C, we've increased the current even more. And it's interesting that when the current gets the highest is actually when the capacitor is completely discharged. So the capacitor would love to stop right here because it's completely discharged, but the inductor would have to immediately cease all of the current flowing through there. And remember, the inductive property of coils means that it can't just do that. So it has to slowly decrease, and that's what we see here in D. But the problem is now we're starting to recharge the capacitor, and so, well, there wouldn't be two charges on there, but maybe I could fix this first one a little bit, make it 3. Maybe we'd have 2 here, none there. And now we've completely charged the capacitor again with the opposite polarity we had before. So that was a little counterproductive for the capacitor. But now we can see that the entire cycle starts over again. It's just kind of flipped the thing upside down. And so it starts to shed its current clockwise to try to get rid of some of the positive charges that now collected on the bottom plate. And eventually it will be discharged. That's here in figure G. But because the the electrical inertia of the inductor means it has to continue to move that charge, and so we're going to recollect some positive charges here on the top plate, and then we're exactly back to where we started again here in figure A. So again, the nature of this is when the inductor is kind of most happy, its lowest potential energy is when the capacitor has its highest potential energy, and that's shown here on the energy bars. And exactly the opposite, when the capacitor is now happy, that means its lowest potential energy, is when the inductor is least happy. That happens in both C and again in G. So what is this like? Well, here's the mechanical analogy. It's like a mass on a spring. You know, masses are happy when they're not moving. Well, unfortunately, that's right here in this figure and this figure, but that's when the spring it's attached to is also the most stretched out. So therefore, the spring is least happy. And the spring is most happy here in figure A when the mass is actually moving the fastest. And so its mechanical inertia means it can't just hit the brakes instantly. It has to eventually slow down. Therefore, we're back to where we have the spring compressed again. So we're going to actually use a mechanical analogy when we do our math as well. So now let's look at the math behind this. So here's a kind of a generic situation. We've got clockwise current shown here, and we can't tell based on the clockwise current whether the capacitor is charged positively or negatively on the top plate. If you go back to that first figure, let me zap back there, there could be clockwise current flowing with the positive charges on the bottom. That would be here in figure F, or we could have the positive charges on top. So I can't necessarily determine, but if I put the positive charges where I put them, then I guess I'm drawing figure H here. So the way I'd like to approach this is by using Kirchhoff's loop rule. And the loop rule says that if I start at one location anywhere on the circuit, I'm going to start here in this lower left or lower right corner, and I completely traverse the loop, then I'm going to get back to where I started, and all my potential drops and my potential jumps have to sum up to be 0. Well, what are those jumps and drops? Well, if you start here and go counterclockwise, we're going to hit the capacitor first. And do you remember how to describe the potential difference across a capacitor? This is the equation I like to buy from the TV shopping network, QVC, and therefore the V is Q over C. That's the potential jump that we would have. And so then we have to have a drop across the inductor. How do we describe that? Well, for this we're going to use basically the definition of inductance, and that is any inductor. You can describe the EMF across it. This is the induced EMF that it makes, which is also measured as a potential difference when you put a voltmeter across it, as minus L di dt. That means not only do we have current through here right now, the current is in the process of changing. And remember that cycle that I showed you a few minutes ago, the current is changing all the time at any point on there. So now we've made it around through the inductor and we're back to where we started, and therefore the total of those jumps and drops have to be 0. And so you might think here, okay, good, I've got myself a formula, I can plug and chug the numbers in there and solve for whatever letter they want me to solve for, but don't be so hasty. This is not just your run-of-the-mill algebra equation, this is indeed a differential equation. And the way you recognize that is to see that the amount of current flowing through the circuit depends on how much charge is on the capacitor. And just looking back here, I think you can see that. When the capacitor was completely discharged, here in figures C and G, is when we had the most current through there. And likewise, when the least current was flowing, is when we had the most charge on the capacitor. So I think the best way to do it is just the very definition of current. What is current? It is the rate, let me write this the way I wrote the other one, the rate at which current flows. So we could describe I as dq dt. I may have said that wrong. The current is the rate at which charge flows, dq dt. But in this case, we have to look carefully at the direction of the current flow. And probably the simplest way to describe this is this Q that I'm using in the equation, that Q is the charge that's actually on the capacitor. Well, this Q is the Q that is no longer on the capacitor. It's actually moving through the circuit. And so the Q in the second equation here is actually what's left. So we have to describe this appropriately as negative dq dt. Think of that as the charge that's leaving the capacitor, the negative sign. And so I'm going to substitute that in for I. And what are we going to get here? Well, we have Q over C still, and then a minus, and then L, and then the derivative of a derivative, dq dt with a negative sign in the front, dt. Now that's a straight up substitution, nothing too exotic about that. But now let's write this out appropriately in calculus. They call this the second derivative of Q. And I was a little careless there using capital Q's and small q's. Let me just, I'm trying to pull a fast one here, but I think small q is going to be better here That way it doesn't look like two different symbols. And that's what we arrive at. Now, the nature of differential equations is you're going to take a class in it if you haven't already, and you're not going to learn so much to solve them as to recognize them. And you'll have names for them like, oh, a second order, and oh, homogeneous, etc. But it helps to have seen a similar differential equation before. And I claim you should have seen this one when we studied simple harmonic oscillators, masses on springs, because we're looking for some function, some q, so that its function and its second derivative are so similar to each other that we could actually add them together to equal 0. But they have to be obviously opposite in sign. So I always ask, well, can you recognize some function that when you take two derivatives of it, you get something that looks almost identical, but it's opposite in sign? And most students in calculus immediately recognize that as either a sine or a cosine. And I asked the same question back when we did mechanical oscillators, and we had masses on springs. And the equation that we came up with there was something like kx plus, and then we had ma, but we wrote a as the second derivative of position. This is a Newton's law equation. It's actually very similar, except instead of a variable x in mechanical systems, we use a variable q in electrical systems. So our solutions are very similar too. On the AP reference sheet, they have equations like the period of a simple harmonic oscillator. And what is that? It's 2 pi radical m over k. Well, there's a period in electrical oscillators too. You just replace everywhere where you would have used an m, that was the abbreviation for, or the abbreviation, the coefficient of the derivative term, you use an L. And over k, well, k was the coefficient of the x term. What is our coefficient of our linear term here? It's 1 over c. So 1 over c is radical LC. So there's a formula you can use just by kind of a one-to-one substitution using electrical symbols in place of mechanical symbols. Well, what I'd like to do here is actually go back to the Q equation and say, well, what could we write as a function? Q is a function of t. What we're writing here is how much charge is on the capacitor at any particular time. And we write this as the maximum Q, that's what we started with, times the cosine of omega t. It's a function of time. We always use omega for what we call the angular frequency, but for these different systems, what does angular frequency mean? Well, in this case, to get this solution to work properly up in the differential equation, it only works when omega is the square root of 1 over LC. So we call that the angular frequency. Just like we had an angular frequency for mechanical systems of radical k over m, now we have sort of an analogous angular frequency for electrical systems. So we could stop there. I think I'm just going to do one more thing. We described the amount of charge. Now, just looking back up here, that's how we know how much charge is on the capacitor. If it starts with a maximum charge, that's how we figure it out as a function of time. We could also take that derivative, though, the derivative of Q, which is the current. That's also changing with time. And so if we take the Q max cosine omega t, we take its derivative, we're going to get the maximum current times the sine of omega t. And I've left the signs out of this. I mean, we're just asked for magnitude, and that's good enough. So that's pretty much everything we'd want to know about an oscillating system. And it's a lot here. We know charge at any particular time. We might want to know current through the inductor as a function of time. We might want to know the period as and how it relates to the inductor and the capacitor we're using. And so you can kind of see how we might use these as timing systems. There's other ways these are used, and I'll have to describe that maybe at another time. But these are the basics of the LC oscillator, and consult your book or maybe replay part of this if you need a little bit more. Hopefully that's been a little bit of a help for you.